So tonight we're going to talk about is Chapter 3, TCP/IP networks. The big thing we're going to talk about is IP addressing. And we're going to talk about that nasty word subnetting, which people kind of get panicky about when they hear the word. I'm going to try to show you a process that I hope is straightforward and quick to do. Lots of videos. I've got some videos at YouTube on how to subnet, different methods how to subnet if you prefer to write, and I'll show you how to write all the ones and zeros and calculate it that way. What I'm going to try to do is show you a process to use what's called the interval, which is much faster. You don't really have to write everything in binary to do it, and it does work. So we're going to talk about IP addresses, the core TCP/IP protocols. We've kind of introduced that already. We'll get more into TCP and IP. We'll look at the header a little bit, and then we can again look at a Wireshark capture to see what is in that header information, because we got all these nice pictures. Here's the header and here's what goes in it. But if we look at what is actually in it, maybe make a little bit more sense about it. And then some common application protocols and ports. The common application protocols, we'll talk about some of those are like HTTP, DNS, DHCP, the things that we need to know about and be able to configure, or at least know about how to configure to make our networks run. And then ports, we're going to talk about. Ports become significant when we do access control lists, when we want to allow people to access specific resources. Maybe they need to get to a web server or a secure web server. What do we need to do? And the ports represent, the port numbers represent applications running at the application layer. And again, applications at the application layer, applications in our sense are, I just clicked the wrong thing. Applications in our sense are, let me turn some lights on. I didn't realize I hadn't done that. Not that you want to look at me, but in our sense are services that are running at the application layer when we do that. So Module A, IPv4 addresses, IPv6 addresses. We're in the process of transitioning from IPv4 to IPv6 in the US. Some parts of the world have been using IPv6 for a number of years because they were simply out of IPv4 addresses. At one point, and we're going to talk about classes, at one point the continent of Africa had one Class C network available to the whole continent. Class C network has 254 usable addresses on it. So IPv6 was a necessity. And then address resolution, and then how IP addresses are assigned. With address resolution, DNS, and host files, two different terms. We'll look at those, and then how they're assigned and the process that we assign. And I'm going to try to show you actual servers that do that. These will be Windows servers. Other softwares have the ability to do that. We can configure these things on a number of different resources. But address space, how many addresses do we have? And we've talked about, and you probably heard about IPv6 and how many addresses it has. And this is a chart to try to kind of put that in perspective. IPv4, 4.29 billion addresses. And we're out of new addresses. I won't say we're totally out of addresses, because some entities that were at the front end of the internet got huge allocations of IP addresses, and not all of them are in active use. But there are no new ones available. And down here, when we go to look at IPv6, and you can see the size of that number, 340 undecillion, 10 to the 36. All sorts of different ways to say that. How many can we have? And I thought that I put it on one of the slides, maybe later on. But it's enough to take care of us for a significant period of time. Let's see, enough addresses to assign 1 trillion to every human who has ever lived. So That'll take care of the Internet of Things for us. We should be able to have enough addresses for a long time. Of course, when they instituted IPv4, they thought that they were going to be sufficient for eternity also. Didn't happen that way, but 340 undecillion, a lot of addresses. Why do we need all those addresses? Just think about it. Even think about how many IP addresses that you have at home. Now, I realize we use a process called NAT, where you actually only use one public IP address, and private IP addresses. We'll get these terms out, and then we're going to talk about what they are here as we go through this. But I mean, you're obviously on a computer. Everybody that's at home, maybe have a tablet, a phone, maybe a TV. A thermostat, smart thermostat that connects to the internet, all sorts of things. Anything that connects to the internet, anything that connects together has to have an IP address. So IPv4, we're out of them. IPv6, transitioning to them, and when we get there, plenty of addresses. You may be using IPv6 at home or not. I am, and I'm going to show you real quick, I hope, what the configuration might look like from your ISP. Spectrum here actually does give me an IPv6 address. If I can get this tab to come over here. I just seem to have lost. Yeah, now it will. When I go to my internet connectivity on this thing, I have an IPv4 address and an IPv6 address. And we're going to call that dual stack when I have both addresses. But they give me, this is called delegated prefix, they give me a network address. So they give me a whole network. And we'll talk about how many of these are when we get there, /64. So IPv6, a thing that's coming, we can have both IPv4 and IPv6 running on our networks, running on our machines simultaneously. They're not going to interfere with each other. And this is where the OSI, TCP/IP, the modular concept of networking comes into play, because we don't have to change the data link layer. We don't have to change the transport layer. TCP is still there. The only thing we're changing is the IP layer. So we can go in, modify the NICs, modify the way the routers send information, and have a complete address. Let me get Blake marked here. So we have that ability to institute, I guess, the stack, the OSI stack, so that, yeah, it worked, because it said that the individuals responsible for that particular section can focus on it, can concentrate on it, and that's what happened. We have a new IP and we're instituting it, and we don't have to go out and buy new equipment, although the hardware has been some modifications to it in order to support these things. But that's been a gradual transition, so that now if you've got a machine, actually a software that supports IPv6, and Windows and Linux do, then we're in business with them. So one of the first things that we need to do is to be able to convert binary to decimal, decimal to binary. I'm going to put a, well, actually I'll try to scroll on this one. Now, yeah, we'll scroll on this one. We don't, or at least I don't, some of you may, but I don't read binary very well. Computers don't read decimal at all. We've talked about, and we've talked about binary and bits and ones and zeros are available to us. And that's how the computer sends its information. It has ones and zeros. That's the way it works. Binary numbers. Again, in the early days, in the really early days, they did in fact try to use decimal on these things. It didn't work. So what we do with IP addresses, they're written in what's called dotted quad. Dotted quad, dotted because we have dots between them, and quad because there are 4 of them. But 192.168.1.0. 192.168.1.0. So we see this. The computer sees something entirely different. It has ones and zeros in it. And here the example 11, whatever this is. So we're going to convert them. We have 8 bits in each of these bytes. So it's going to be a 32-bit address. 32-bit address that the computer reads in binary, in the dotted quad. What we need to be able to do some of the networking that we're going to do is to be able to go back and forth. These columns here, 1, 2, 3, 4, 5, 6, 7, 8. In each of them, we can have 2 values. It can be a 0 or a 1. And that's pretty handy. And then in all of this stuff, if we can multiply by 2, we're in great shape. So in the first column, this 2 to the 0, what is the value? It can be a 0 or a 1. So it can be 0 or 1. In the next one, the next column, the value here, how much it's worth, the placeholder, is a 2, 4, 8, 16, 32, 64, 128. Okay, so if we have 1 bit, the value of it is 1. The maximum value of it is 1. If we have a 0, obviously it's going to be 0. So we have 2 possibilities here, 0 and 1. So 2 is how many can we have here is going to be 2. And how many can we have here is going to be 4. And all of these things, we just double them. And the second one, just to show you what it would be, and I don't go much further because I get confused. But the value can be 0, 0, 0, 1, 1, 0, or 1, 1, which gives me 4 different possibilities in this column. The next one is 8. I probably can do this one too. It can be 0, 0, 0, 0, 0, 1, 0, 1, 0. Just keep adding 1 to it. 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1. Did I get 8 there? 1, 2, 3, 4, 5, 6, 7, 8. So how many? The next one I'm not going to attempt. 16. We just double it each time. 32, 64, 128, 256. So the 256, the values that we can have totally if we add all of these placeholders up is going to be 256. 0 to 255. In networking, 0 represents something. It's not the null set. So when we want to convert from one to the other, and when you go in to do testing, if you want to be able to do any conversions quickly, just write down a quick table. 1, 2, 4, 8, 16, 32, 64, 128. And then somebody gives you an IP address. If you get the binary here, 1, 1, 1, 1, 0, 1, 1, 0, 1, 0, the way we convert that 1 times 128 is 128, and these are down here. I'm going to write them here, 128. 1 times 64 is 64. 0 times 32 is 0. 116, 1, 8, 0, 0, 4s, 1, 2, and 0, 1s. When we add those up, just add those numbers up, and you will have converted from binary to decimal, in this case 218. Same thing down here, 157. So what if we want to go in the other direction? What if we want to, let me get rid of this mess that I'm making, go into the other direction, and let's just pick a number, any number. Anybody want to pick a number for me? Between 0 and 255? Somebody want to put one in the chat? Or I can pick one. 211. Okay, good deal. 211. We have our values here. What we would do is we start with 211. Is 211 greater than or equal to 128? The answer is yes. We put a 1 in that column. And then we subtract 128 from it. 3, 8. Is that right? Did I get it? 8 3 is 11. 8 2 is 10, 11. So 83. Is 83 greater than or equal to 64? Yes, it is. Put a 1 in that column. Subtract 64 from it. 9 and 4 is 13. 19. Is that right? Yeah, because 84 would be 20. Is 19 greater than or equal to 32? Nope. So we'll put a 0 in here. Is 19 greater than or equal to 16? Yes. And so we'll subtract 16. We get 3. Greater than or equal to 8? No. Greater than or equal to 4? No. Greater than or equal to 2? Yes. And then we subtract 2. Greater than or equal to 1? Yes, 1. So convert 211, and you probably have a calculator there on your computer that you can check me on this. 211, binary should be 11010011. Not a problem, Blake. Got it. We're doing good. And I understand that. Tonight, we're obviously in 4. I'm actually recording this one because they're having extreme weather in Colorado. And a lot of them aren't able to get here. But anyhow, binary to decimal conversion in order to do that. Binary to decimal, does it make sense? If it doesn't, we need to do some more. Somebody needs to ask a question about it. Going once, going twice. Anybody comment? Let's say, everybody comment, yes or no. I can do binary to decimal conversion. Because this is step 1. We got to get this down. Not getting a whole lot of response. Okay, I got a no. Good. So, you're going to have to ask me a question, Joe. Because all it is taking this, and let's go back again. Does the weight or the value make sense to you? Okay. So what we have is either we're activating that column, the value in that column, or we're not activating it. We're either going to use it or we're not going to use it. We have 8 bits in our numbers and dotted quad when we do those things. But if we have a binary number, we have to use this weight table here, or value table, or placeholder table, whatever we're going to talk about. And then we just write the binary number underneath it. Does going from binary to decimal make sense? Okay, the decimal to binary, not a problem. That's what we needed to do. So let's do that. Give me a number, any number. 0 to 255. 255 don't work out real well, but we could do that too. Nobody wants to do it. I'll give me a number, 187. 154, okay. We'll do 154. 154. So, in these things, we add up the weights here to get the decimal from the binary after we say which ones are active. So in order to add these up, we got to have a 128 in here. Is 128 or is 154 the number that we started at greater than or equal to 128? And the answer is yes, because if we added all of these numbers up, it's going to be 127. 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. That would be a 127, and then we're going to struggle to get to the number that we want. So is 128 or is 154 greater than or equal to, is 128 less than or equal to 154? So, and the answer is yes in that case. So now we got to take the 128 out of the decimal number. So we subtracted here 6, and this will be 4, 2, 26. And if I get my arithmetic wrong, please yell. So is 26 greater than or equal to 64? The answer would be no, so we're not going to add a 64 in here. How about 32? No, so we're not going to add a 32 in here. 16? Yes. We'll do a 1 and we'll subtract 16 and get 10. Is it greater than or equal? Is there an 8 in here? And the answer is yes. So we subtract the 8 and we have 2. Is there a 4 in here? No. Is there a 2 in here? Yes. Is there a 1 in here? No. And the 1 here, the little tipper here is, if it's an odd number, you should wind up with a 1 in the last column. If it's an even number, you should wind up with a 0 in the last column. So let's add these things up and see if they work. 128 plus 16 plus 8 plus 2. Did I get everything in there? 8 and 2 is 10. 16 plus 8 is, 16 plus 8 is what, 24? 14, 24, carry the 2. 2 and 2 is 4. 5, 154. So it does work when we get there. Okay, so Joe wants to go from, we'll do that. We want to go from a binary, and our binary is 1, 0, 0, or was that the one that we had? 1, 0, 0, 1, 1, 0, 1, 0. Is that the one we just had, Joe? As I looked down, I had a binary in here. 1, 0, 0, 1, 1, 0, 1, 0. Yeah, that's it. So that's the number, and yes, if that's what you're asking, that is the binary representation of 154. So does it make any more sense? Does it make some sense? Can you convert these things? And again, this is one that I kind of need a yep, so that we can go on. And unless somebody speaks up, I'm going to take it as a yes, that you can do these conversions from one to the other. Binary to decimal, decimal to binary. The key to me is the chart. 1, 2, 4, 8, 16, 32, 64, 128. Okay, and then what do we have? Each of the octets in our dotted quad is going to be made up by 8 binary numbers when we do that thing. So we have the convert from one to the other, convert back and forth in order to do these things. IP addressing, we're gonna have some slides here, and then we'll get into some other arithmetic that we'll use some of that with. But it was first deployed in 1983, so it's been around a long time. DoD was the first one, the ARPANET, DoD ARPANET, Advanced Research Project Network, invented, and they did invent the internet. They invented networking. They are the ones that came up with the addressing scheme, how to use the addresses, how to make the addresses hierarchical so that we could actually do routing and get from one to the other. If we had a helter-skelter arrangement of the assignment of these addresses, and yours was close to mine, the routing tables that we would have to have would be so big that the routers would never be able to process them. So they use hierarchical. And if you look at on your internet, in your neighborhood, yeah, everybody's going to be on the same, what we're going to call subnet, or the same network, the same IP network when we do these things. So we have those. ARPANET, used to route information on the internet. 32-bit binary address, we looked at that, called a dotted quad. For readability purposes, the dotted quad, so that we can read them. The writing them as the dotted quad is for us. It's not for the computer, obviously. Computer needs to have binary, and actually a lot of it's going to be written in hexadecimal. At least a lot of the interpretation is going to be in hexadecimal. Two parts of the address. We haven't talked about that yet. One of them's going to be the address itself, the 192.168.1.0 or 1.2 or 1.3 or whatever. The other part written underneath it is this thing called the subnet mask, which is a string of zeros or string of ones followed by a string of zeros. And what we do with that is tell the computer how much of the address is network and how much is unique host identification. And a lot of people have talked about this in light of regular addresses, street addresses, where the network address would be your street and the host portion would be your house number, or that an apartment building, that the network portion would be the address of the apartment building and the host portion would be the apartment numbers within the building. So we're going to have two parts of that. The internet, the routers route to, and I say subnets, route to networks. And then we're going to have a different protocol that we're going to look at in order to find the individual device. And the individual device is going to be identified, and we talked about last night, by its MAC address, its media access control address, the one that is going to be unique to it. So addressing, every network interface needs an IP address to send and receive packets. 32-bit number, dotted decimal notation, dotted quad, dotted decimal is used to write the address. 8 bits, an octet in each of them in an IP address converted from binary form to decimal form. We saw how to do that conversion. The decimal range of each octet is 0 to 255, which gives us 256 numbers because 0 counts. And 0, the one where all of the host bits are 0, where we have a 0, all zeros in the host bits, and I won't say A0 because in some cases it will be, in some cases it won't. It's going to be a special address called the network address. Written like 192.1.1.1 is an example of an IP address in dotted decimal notation. Not a real problem. We have IPv4 addresses here, and these are actually written out in the beginning. We had addresses without subnet masks. This one has got a subnet mask. Later on, we created a thing called CIDR, which is classless internet domain routing, which then meant that we could break down our networks into smaller components. But originally, we had 3 assignable classes, 4 total of classes. We had a class A, a class B, and a class C. And I've got a couple of slides that I think will show this a little bit better. But in the class A, in the dotted decimal notation in the quads, the first address is the dark blue. This is going to be the network portion. And then we have a host, and a host. And this has somewhere around 16 million hosts, or 16 million addresses. It's 16 million something addresses in each network. If you know anything about Windows, that's impractical from a broadcast point of view. The next, we had class B addresses, which we had network, host, and each of these had like 64,000 networks and 64,000, 65,000 hosts on them. And then we had class C's, which we had a network part, a network part, a network part, a whole lot more networks. And in the host part, we could have 0 to 255. And in this one, the 0 is a special one. It's going to be called the network address. And the 255 is a special one called the broadcast address. And we talked about broadcast. We talked about the MAC broadcast, which was all F's. FF, 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 FF. I think I've got the right number in there for that one. So broadcast address, special addresses. And this one down here, so IP address shows it in binary, and it shows it, this down here shows this thing written in binary. And then the subnet mask is a 255.255, which means that it's going to be a class B. But when we AND, we call it an ANDing process. Well, a 1 and a 1 is a 1. A 1 and a 0 is a 0. Boolean algebra when we do that. So all of the network part, the network ID is under the 1s in the subnet mask. So the 1s, and good idea when you're doing these things, draw a line, and I can't do a straight line, a nice wiggly line there, a line between the network portion and the host portion. So we have all network. The network portion is the thing that has 1s underneath it in the binary representation of the subnet mask. The host portion is the thing that has 0s under it in the subnet mask. And obviously when you AND 0s with anything, you're going to get 0. So that's where the network ID is going to be. This one over here, we have a different number. This is a 192 and probably a 168. But we have the class C subnet mask, the network. So we have the network portion of it is the first 3 octets and then all 0s. And the 0 address here is still going to be the network address. The host, and they just did host down here. I don't know why they did that, but the host address itself is going to be, I don't know why, 010. Yeah, 00 is going to be this. So if we wanted to know the host portion, obviously, well, we could do that. The reason that we kind of need these things in binary, and while we got it here in binary, the first address that we can assign to an entity, to a host, is going to be the network address plus 1. So this one would all be 00001, because the last in our 1, 2, 1, 2, 4, 8, 16 on down the line was 1. The broadcast address is going to be where the host address is all 1s. And the broadcast goes to every station in that network, in that subnet. And if we have all 1s here in a single octet, it's going to be 255. The last address that you can assign to a host is going to be 1 less than the broadcast, which would be 254. So the assignable addresses, the ones that we can go in and type in the IP address, will be, and I'm going to assume this is 192.168, and I didn't do the conversion on that, whatever the network address is. That's a 6496. 124, maybe a 100. Does that look right? 192.168.100.1 would be the first one. 192.168.100.254 would be the last one that we could use. 192.168.100.0 would be a network address. 192.168.100.255 would be the broadcast address. So different ways to do that. And yeah, this is a drink with a bigger fire hose tonight. The classes that we have, this one shows the classes along with the with the representation of the subnet mask. So the class A, network, and I spell network wrong, it's a netwalk here, it should be network. Network, host, 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 like we said in the octets themselves. The subnet mask 255.0.0.0. Class B, 255.255.0.0. 2 octets for network addresses, 2 octets for host addresses. The Class C, 3 octets for network address, 1 for host. And down here, the ranges as well as the way the binary starts, because if you get into a situation, particularly in a testing environment, and they say, okay, what class is this one? And I don't remember it's 0 to 127. What I remember is it starts with a 0. And if I did a 0 in my 1, 2, 4, 8, 16, 32, 64, 128, and I add all these up, it's going to be 127. Quick way for that, if we have 1s in all of these things here, it's going to be 1 less than this number. So, and that one would be a 0. So 0 to 127 starts with a 0. The /8 is called CIDR notation, classless internet domain routing. And that represents the number of zeros in the subnet mask. In the subnet mask. So, a couple of things here. First octet, the class. The high order bits where we start. The class B address are going to start with a 1, 0. Hey, 128, that works out. 1, 0. And then it's going to go to 1 less than the next one, is the way I remember it, which is 1, 1. It's going to be a 192. And the class D, which is going to be multicast addresses, are 1, 1, 1. And the class E, which experimental, military, reserved, anyway, we can't use them. There's going to be 1, 1, 1. And then how we get these things, how we create each of the circumstances here. Special address ranges, the 0.0.0.0 is a default route when you get to routing. 127.0.0.0 is a loopback address. We use the 127.0.0.1. So 127 is actually taken out of the class A. The assignable network addresses are 1 to 126 because 127, an entire class A network with 128, 16,777,214 addresses, we use 1. And the range of the private IP addresses, we've alluded to that. Private IP addresses are those that we use. And if you look on your network at home, it's probably going to have a 192.168, either a .0 or a .1 for its internal IP addressing. And I think if you're at one of LeaderQuest facilities, it's going to be a 10 something, and I don't remember what they are, but I think they use the 10 addresses here. So we have private addresses that we can use inside of our networks. Anybody can use them, everybody can use them, whichever ones that you want. They're not routable. They'll never appear on the internet. In order to get on the internet, we use a process called NAT, Network Address Translation, where we translate the private address to a public address. So we have that possibility. The other special thing we have here is a PIPA, Automatic Private IP Addressing. What that says is most of our addresses come from a process that we'll look at called DHCP, where we automatically get an IP address. You probably don't type them in at home, and you certainly don't type them in at LeaderQuest. They get assigned automatically by a process called DHCP, Dynamic Host Configuration Protocol. If we get this 169.254 address, what that says is my computer's trying to get an IP address from DHCP, but I can't talk to the server, so I'm going to give myself an address. You can't get out of your local network with that address. So you get an address, but you can't go anywhere with it. Am I making any sense so far? I hope. This is one and we talked about these last night. We had the same sort of arrangement in the hardware addresses, in the MAC addresses. 3 different types, and this is for IPv4. When we get to IPv6, it's going to be a little different. So we have one sender, one receiver, unicast, 1 to 1. a broadcast, and I talked about the broadcast address. It is in IP, is the one where the host bits, and I keep saying the host bits because we're going to talk about subnetting. It's not necessarily going to be a classful address. We may decide that we need more networks, fewer hosts, more hosts, fewer networks, whatever, however we're going to do it. But when we send it to all of the stations on our network, it's going to be called a broadcast. So it goes to all of them, and then a multicast goes to the select few. They talk about subscriptions. Where I've seen this used mostly, the multicast used mostly, is in routing protocols. So that if we have OSPF routing protocol, all routers that have that protocol running on it are in a multicast group, have a multicast address so that they can share route information. So that is where I have seen it used a lot. And I said earlier, originally we didn't have any subnet masks. We had the class full addresses, the Class A addresses, the Class B addresses, and the Class C addresses. Then we added the subnet mask. We, the smart guys that actually do the addressing, added the subnet mask to tell us how much of the network is network portion, how much of the address is network portion, and how much of the address is host portion. When we subnet, we change the subnet mask. No big deal. Subnetting is, and I got a buddy who said, this is the way I do it, so I'm going to try it out. If you have $1, which would be your network address, and you break it up into 4 quarters, you still have $1, but it's in 4 segments. Same thing happens with subnetting. We have a network address. We're going to break it up into initially equal parts when we do this thing. So we're going to modify the bits in the network and the host portion. We're going to show you how to do that, and then show you what I think is an easier way to do it. So what you need, and this is a chart by Cold Iron, what we have is our 8 bits that are in each of the octets. Bits 1, 2, 3, 4, 5, 6, 7, and 8. And then we have the value or the placeholder. And I said how many, and this is how many if we add up all of these things. We can add how many how many are available in each of these: 2, 4, 8, 16, 32, 64, 128. This is actually a 2 to the power. 2 to the 1, any number to the first power is 2. 2 to the 2, 2 to the 2 is 4. 2 to the 3 is 8. 2 to the 4th is 16. 2 to the 5th, 32. 2 to the 6th, 64. 2 to the 7th, 128. And 2 to the 8th, 256. So how many, and the reason how many, when we start breaking this thing up, how many subnets do we want to have? First, I want to do the writing it in binary. So let's say that we have 192.168.1.0 network with a 255.255.255.0 subnet mask. A Class C. I like to do the Class C because the arithmetic's easier to do, and I don't make as many mistakes. So let's say that, the network administrator or your boss or whoever comes in and says, we really need to break up our classrooms. And we had to do this at ECPI because we initially had everybody on a great huge network. And what would happen in the Windows classes, you get people coming in just starting with the Windows client, and then you got people in the server been doing it a while, and they've figured this thing out. They would find the new students, and in the labs, everybody's got the same username and password, and they do things for them. When we decided to break this up, we then didn't have that problem anymore. All of the advanced students were on the advanced student network, all of the beginners were on the beginner network, and on down the line, the intermediates on the intermediate network. So that's where the how many comes in. How many do I want? Let's say I want 4. Then I need 2 bits to make 4 networks. What I'm going to do, and all of these are 1s, and when we do subnetting, the only octet that you need to worry about is the one that you're actually working on, the one that you're subnetting. So we have this thing, and our subnet mask initially is 0, 0, 3, 4, 5, 6, 7, 8. What we're going to do is to increase the number of subnets, and when we do that, we're going to decrease the number of hosts per subnet. So I said I needed 4 of these things. How many? 4. I need 2 bits. What I do is move the subnet mask to the right 2 bits so that the subnet mask is now 1, 1, 1, 2, 3, 4, 5, 6, which gives me 6 bits for hosts, 2 bits for subnet, and I'm in business. The network subnet possibilities are 0, 0 in this bit, 0, 0 here just like it is, the 0, 1, 1, 0, and 1, 1, which gives me my 4 network addresses, and they are here 0, 0, which is 0, a 0, 1, which is 64, a 1, 0, which is 128, and a 1, 1, which if you add those up is going to be a 192. So we can write the binary. Kind of a quicker way, I think, to do it is they tell us that we need 4 networks. How many? 2 bits. So I know I have 8, so I've used 2 bits. I started with 8. I used 2 bits for the network, to create my network. So I subtract 2. That leaves me 6 bits. When I go over here to the 6 bits, it says that each of the networks is going to have 64 addresses on it. So I can start out, I know my first one's 0, and I add 64 to it. 64. I add 64 to this and I get 128. I add 64 to this, I get 192. These are my network addresses: 192, 168, 1.0, 1.64, 1.128, 1.192. What are my usable addresses? The first one here, 1 plus the network address, 1 on this network, 65 here, 129 here, 193 here. What's my broadcast address? And this is the one that gets tricky but easy, I think. The broadcast address is 1 less than the next network address. So the broadcast address here is going to be 63. The broadcast address here is going to be 127. The broadcast address here is going to be 191. And if we add this one up, this will be 256. The broadcast address here is going to be 255. Last usable, 1 less than the broadcast. 62, 126, 190, 254. And those are typically the things that they'll ask you on subnetting questions. Now that we've done that, somebody give me a problem to subnet. Tell me what network you want to start with and whether you want to do hosts or networks. You can do one or the other, but you can't create more bits. You have to have the 8 bits. And one of the other things, if I had one that I needed, let's say I needed 25 hosts. If I needed 25 hosts, I've got to go to 32 because there is no 25 in the how many here. 25 is in here, 16's too few. I need to go to 32. If I needed 32, remember, you can't use two addresses. So if I needed 32, I got to go to 64, because the most that I could assign here would be 30. We have to subtract two addresses from each of these. So how many or what? Which one do you want to do? How do you want to do this one? So give me a problem, and let's see if we can work it. Anybody up for that? Nobody wants to give me a problem. You want to subnet a network. Tell me either how many networks you want or how many hosts you want per network. I tell you what, let me pause this. Okay, I want to continue, and for those who aren't here tonight and getting the link to the video, in the student share that you have, and I'll put a link to, I'll put its link in the email that I send to you, is in the IP information folder is an IP address and subnetting for new users. This is a Cisco document, the instructor subnet workbook. It goes through a lot of different things step by step with exercises that you can do on this. It starts out with the addresses, with the classes, the default subnet mask, those things, and then goes into binary to decimal conversion, decimal to binary conversion. The greens are the answers to the, obviously the others are. If you want to work on them and then come back and check your answers, there's a student workbook. It doesn't have the answers in it, and there is a then you can come back and check it with the instructor workbook. Address classes, identifying the classes of addresses, and then how much is network and how much is host when you go through those things. Network address, using IP, using the IP address and the subnet mask, how much of it is what, so that you write out the network address on each of them. A number of exercises that are available if you want to do them. We'll talk about IPv6 a little bit. There is also an IPv6 workbook in there. VLSM, which is going to be the topic after we do this one more subnetting problem, also has a workbook. So lots of, or at least some subnetting help here. So none of you came up with a network that you want to break up, so let me see if I can make one up here. If I can find my pen for this thing. I know I told you early on my handwriting is horrible, and it is. Let's say that we have a network 192.168.10.0 with a standard subnet mask, which is 255.255.255.0, and let's say that we want to break it up with, let's use the 25 hosts per network. To get to 25 is in between here. We've got to go to 32, which means that we have 5 bits for hosts. So the host portion is going to be 5 bits, and if we write the subnet mask, it's going to be 1, 2, 3, 4, 5 zeros, which leaves us 1, 2, 3 ones. So we have 3 ones, which we have 3 bits here. 3 bits means that we're going to have 8 networks available. Since we have 5, and I just want to do the increment method. So each of the networks is going to have 32 addresses on it. We're going to start out with the first one will be 0, the next one 32, 64, 96, 128, right? Yeah, 32, 9, 10, 11, 12, 128, 32, let's see, 8 2 is 10, 3 and 2 is 5, 6, 160, 192, 4, 224, and then 32 would be 256. So 1, 2, 3, 4, 5, 6, 7, 8 network addresses. First usable, host plus 1, or the network plus 1. The last is the next network minus 1 is going to come up here to be the broadcast, in this case 31. The last usable, 31 less than the broadcast. First usable, 1 plus the network address. So we have network address, first usable host address, last usable host address, and broadcast address. Hopefully a fairly straightforward process to do these things with. Okay, so I'll get it. There are other situations, and now that we've done those things, and then we've done it a couple of times. We have a network here that we've got an uneven number of hosts that we need on each network. This is called VLSM, variable length subnet mask. These that we did back here were all fixed length subnet mask. Everything had the same number of addresses in it. And back to our change for $1. You could do 4 quarters all equal. You could do 2 quarters, 3 dimes, and 4 nickels. So we would have a different number of coins, a different number of pennies in each of those. We can have a different number of hosts in each of our subnets. So, and it's going to work the same way, or I'm going to try to work it the same way with the what we've called the increment. The increment is how many addresses there. And when you do a variable length, you start with the largest, with the one with the most hosts in it, largest, and then you work your way down. And then this one, 60, we're going to do it first, and then 30 will be second, and then 12 will be third. So to do that, get rid of some of this stuff. To do that, when we go in here, and we'll go back up and use our chart. To get 60 hosts, hey, 6 bits, right? 6 bits to do that. So we could write the subnet mask. So the host is 6 bits, which means that we've got 6 ones, 1, 2, 3, 4, 5, 6, 7, 8 for the network portion. So we move the network portion over to the right. The network address 173.35.4.0, the first network that we're going to do, the 60 hosts will be on the 173.35.4.0. But now this was a 24. Remember the /24, we added 2 bits to it, so it's going to be /26. We're going to, since we used 6 bits for host, we're going to have to take out the 64 addresses that we use there. So the next network will start with 173.35.4.64 because our increment was 64. And it's going to have 30 hosts. 30 hosts, 32 works for that because remember we have to subtract 2 off of those. This one's going to have a maximum of 62. We're okay with the 60. This one needs 30. We subtract 2, so 30 hosts here, 32 total addresses, 5 bits for host. So we have 1, 2, 3, 4, 5, which leaves us that I did that backwards. So let's get rid of those and let's do it frontwards. 5 bits for hosts. I did this one backwards up here too, didn't I? But the host should have zeros and you guys let me do it, 1, 2, 3, 4, 5, which then leaves us 3 bits for network. I'm going to erase the wrong one because it drives me crazy. So I did it backwards, the ones and the zeros, but we did the bits right. So this one adds 3 bits to the subnet mask so its CIDR address will be /27. We took out 32 addresses. We now use 32 more addresses. So we had 64 was the last network address, 64, and we used 32 addresses. So now the next network address will be 96, 173.35.4.96. It has 12 hosts. 12 hosts, we've got to go to the 16, 4 bits. So it's going to be 4 of each. When we add 4 to the original subnet mask, we're going to have a /28. So we have done a variable length subnet mask. We have these things here. Each of the networks got a different number of hosts on it, but we still haven't used all of our addresses. I mean, we've got a lot of addresses that we could use. What you're basically doing here, and the next one would be 16. We would add 16 to the 96. 9 was 10, 11, right? 112. So the next network address would be 112 when we do that. And so we can keep going, adding these things, unequal number of addresses on each of the networks. And again, that there is in the share is a VLSM workbook also. I guess if I got the mouse it would work better. But down here, a student edition and an instructor edition. I'm going to open the instructor edition, bring it over, take a look at the things that it does. It starts out the same way. Then it talks about classful subnetting and visualizing subnets with the box method. This box method may or may not work for you. VLSM addressing. I like the increment method because you can do it very quickly once you've practiced it. And subnetting is something that does take practice. It's not something that you're going to just, well, it is something that magically happens after you have practiced it and practiced it and practiced it, and you say, oh, it's pretty straightforward. Yeah, 112/29, exactly, Joe. Because, yeah, which would be, these are the special IPv4 addresses. We had those on one of the slides a little bit earlier. The 0.0.0.0 is a default route, and that would be used in routing, of course, when we write a default route, gateway route. The default route is one, and when we're doing routing is if nothing else works, that's the one we do. The 255.255.255.255 is a broadcast to anything. A network broadcast address is the one where the host bits are all ones, and that's why I tried to stay away from the 255. That works for the class full networks, but we did the subnetting, and it's going to be a different address. We saw the addresses. We had the 0, 32 would be a network address, then 31 would be the broadcast address of the previous network. The 127.0.0.1, we take an entire class A subnet, 16 million addresses, and use one of them as the loopback address for troubleshooting. We had the private ranges. The private ranges, the 10.0 with the 255.0.0. The entire 10 network is a private address. Private addresses, anybody can use them, don't have to pay for them, but they're not routable on the internet. The class B is a 172.16 to 172.31. So we have 16 plus 16 here. We got 16, right? If I did that right. 32 would be the next one. So 2, 4, 8, 16, 192, 222, 224. 240 is going to be the subnet mask on this one. The 192, 168 with a, yeah, it is 240. I didn't see it over there. I did the calculation. With the 255, 255.0.0 is the class C. So all of the 192, 168 can be masked using the class C subnet mask 255.255.255.0. We can use all 192, 168 numbers as class C addresses. The last one down there, the 169.254, is the APIPA automatic private IP addressing. Again, if we're trying to get an automatic address assignment, a DHCP address assignment, we can't get to the server, then the workstation is going to give itself an IP address, and it'll be a 169.254 with a 255.255.0.0 subnet mask, and it won't have a default gateway. It will not allow you off of your network. The next topic is IPv6 addresses. They look a little different. And we talked about EUI 64 addresses last night a little bit, and the tipper here is the FFFE here in the middle of this thing. So EUI 64, we're going to have the prefix. The prefix, when you hear prefix, think network address. And then we're assigned a prefix. We can create a subnet. Once we got the prefix, we then assign our IP addresses. So the prefix we can subnet by putting addresses in there. Use the 12E0. You could use 1, 2, 3, 4, whatever you wanted to do once you got the prefix. And I showed you that my ISP has given me a prefix. We can go back and look at it since not everybody was here at the time, because of various things, part of it weather. So when I bring this thing over here, the SageCom, and when you see SageCom, you know where that name's coming from now. This is Spectrum. I have an IPv4 address. This is the routable one, the 72.131.4.8. And you notice the subnet mask 255.255.224.0. So you can go back in here and do your own if you want to do it. How many addresses are on this subnet, on this network, in this neighborhood, basically, is what we do. And I've manually specified DNS. I use OpenDNS, which you may want to consider because it allows you to block categories like adware, things like that. But I turned on the IPv6, and lo and behold, I got a delegated prefix. They assigned me with a /64 a network address. So I own this network internally on my network. All IPv6 addresses are public, no private addresses on this thing. So 64, it leaves me 64 bits for host. Man, I could have a big network, except I can't have a big network because I don't have enough hosts, don't have enough routers, don't have enough a lot of stuff. But they assign it, ISPs assign the IPv6 addresses. And we talked about the 340 undecillion, and it's enough to assign 1 trillion to every human who's ever lived on Earth. So lots of addresses out there. The addressing scheme, 28 bits, 16 bytes, 8 hexadecimal blocks. We don't write this thing in binary, we write it in hexadecimal. Hexadecimal is really a shortcut for binary. If we had a number here, let's say DB, let's say DB 64, let's say AB. How about AB? AB. What it is a shortcut for binary. The way hex goes is 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, which ends at 15. A is going to be 11, right? No, or 10. A is going to be 10. What we do, shortcut way, quick way to do hex conversion is to write it in a binary. So if we have our two parts, 1, 2, 4, 8, 8 4 is 12, 8 and 4 is 12, 1, 2, did I do that wrong? 12, 14, 15, I can't add, I did 8 and 4 is 12, 16, 17, so that's not working, 8 and 4 is 12, so we have 4 bits in these things to get to 15. So if I write an A as a 10, which is an 8 and a 2, would be 1, 0, 1, 0, right? And the B is 11, and its binary would be 1, 0, 1, 1. So I have now created an 8-bit binary number from the two halves. And if you get a binary number, split it in half. Almost got a straight line. Split it in half, and then do 1, 2, 4, 8. Find out what its value is. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Quick way to do those conversions. The thing that you typically see on IPv6 is how to write a legal address. We have the full address here, has all this stuff. There are some rules that we can do. We can remove the leading zeros from the first 3 positions. So in this one, we can just not write those 3 leading zeros, those 2 leading zeros, those 3 leading zeros. So, and this one down here, the IP abbreviated 2001DB8 0560 ABCDEF 12 1 2 3 4. A lot quicker. The other thing that you can do is if we have a string of zeros, and I'm going to put more than one octet in here, or more than one number in here. It's not an octet. It's 16. If we have a string of zeros, we can represent those with a colon colon one time. One time because if we did it more than once, it wouldn't know how many zeros we replaced, but the system itself can do that. What they've done here is the first one here, the first string of zeros with a 0, the second one with a colon colon. So you can do that, but if we had consecutive zeros, we can replace them with a colon colon. Right here, in this number, this bunch right here could be replaced with a colon colon. And a lot of times you'll see the prefix written on down the line, and I think probably mine was, it had a prefix, and then a colon colon, and then it was a /64, which meant that the first 64 bits belong to the CIDR notation. The first 64 bits are network address. Everything else, which leaves 64 bits, is going to be host address. Same thing down here, 64 bits in the network at a 48-bit prefix, and then a subnet 12 here. This address would be 64 to tell us that we have 64 bits in the subnet mask. And these I just threw in so that you can see, yep, these are what they look like. The binary, yeah, the prefix, the binary, the description of what they are. This is just a slide that I found somewhere that I use in some other classes to so that you can see about prefixes and the CIDR notation / and then what it looks like in binary for these things. And you notice these down here, all of these, we write the prefix and then a colon colon /23, how many bits are in the network address, in the prefix. And these are some, the 2600 are the ones that are, mine was 2605, I think. 2600s are the ones that are being, AREN is the North America, that are being distributed in the different parts of the country. The types of IPv6 addresses, in IPv4 we had unicast, we have unicast again. We had multicast, we have multicast again. And then we have this thing called anycast, and I've got another slide here in a minute that hopefully kind of anycast will make some sense. But in words, what anycast is, we can have an anycast address on multiple resources, multiple servers, multiple Google lookup locations. And when we go to one of those addresses, the routers will send us to the one that we can get to most efficiently. And down here at the bottom, there are no broadcasts in IPv6. So the broadcast address is no more in IPv6. And when we do this, another kind of extra thrown in here, unassigned 0::0. The loopback address, I think only easy address to write in this thing is ::1. The link local addresses, link local are automatically assigned by the device. And let me look at this machine here, if I can get a command prompt. Let's see, or not. This machine's got a lot of stuff around. It's got some virtualization, so I get a lot of stuff. But the Ethernet adapter that I'm using right now, I have the physical address 1C3947C99A00, 48-bit address. DHCP enabled, yes, I'm getting them automatically. Auto configuration enabled, yes. And we'll talk about auto configuration. We might as well talk about it now. But auto configuration in IPv6 sets the router up so that it sends the workstation the prefix, the network address, and the workstation then configures its own or creates its own host portion of the IP address. Doesn't use DHCP. Auto configuration, of stateless auto configuration does not anyway. So we have that ability, and the IP address 2605A0001407A412:0, and this we got the 1, 2, 3, 4, and 1, 2, 3, 4. So the prefix that they assign me is here. It is a 2605, and then the last half of it is going to be the host portion of the address itself. When the lease was obtained, when it expires, IPv6 address, again here, it's the same prefix, but now I have a different address, and I don't know why I have two, but I do. I do too, because I was fooled. It stopped giving me automatic addresses at one time, and I assigned my own. But I'm getting two IPv6 addresses. I have a link local address. Link local addresses start with FE80. They're the things that replaced broadcast. Actually, they didn't replace. I don't want to say that. They find local neighbors. Link local within the link, within the broadcast domain. They find the neighbors and make a table of them so that they'll be available to them. The default gateway, you notice, is a link local address. IPv6 internally, for routing purposes, default gateways don't use the public address or the public address. Yeah, we'll say the public address in order to go from one location to the other. So we have the link local. We have some unique local, multicast, and global multicast, different addresses, but in them there is no broadcast address. The link local, usable on the local segment, it's not routable. Site local, if you want to set up addresses within a site, you can do that. They're routable within an organization, but not globally routable. The global routable address, the 2000, that was my 2605 address, is routable on the internet. And global routable, every IPv6 address is a global routable address. Every device that gets IPv6 gets a global routable. After I said that, yeah, we still have the site local and link local additional addresses, but there is no NAT, there is no private addresses in IPv6. And we have multicast addresses. This is just, yep, they are kind of what they look like. The multicast addresses start with FF02. You can see all those things. And I said, what I have seen them mostly is in routing protocols, and then all routers, all hosts and routers that in the network to support IPv6, routers in the network to support IPv6, and then routers that are running EIGRP, the FF02::A, the OSPF, FF02::5 and 6, and those are two different types of routers in OSPF that support that. Address identifies that identifies many interfaces on the network. A multicast address, first 6 bytes is FF. So the verbiage here, I think, is the same thing that I was saying over here. But FF02 are the ways these are going to start. This is kind of an image to try to show what an anycast address is. An anycast, here we have an anycast on these 3 different routers, and if I'm going from one location to the other, my router is going to have a cost to each of these things, and it's going to get me to the one that has the least cost, get me to the one that is most advantageous to me. Migration, we are migrating from IPv4 to IPv6. Dual stack means that we have both IPv4 and IPv6 addresses, and when I did the IP config, and you saw in the command prompt, there were both version 4 and version 6 addresses there. If the system can use a version 6 address, it's going to. They are more efficient, they're more secure, and just generally a simpler, better to use protocol. So if it is available, if I go to a website and it has IPv6 enabled, system will detect that and it's going to use IPv6 to get there. Translation, these are just some other ways to do it. Translation uses protocols like a NAT64 to connect IPv6 to an IPv4 network like conventional NAT, so that it's not using a dual stack. I think that at least all Windows and all Linux are using dual stack, so it shouldn't be an issue with this thing, but it can translate from IPv6 to IPv4 and IPv4 to IPv6 to talk back in the other direction. Another way is tunneling here, where we have IPv6 here and IPv6 here. We send it through an IPv4 wide area network. What you actually do is put an IPv4 address header, encapsulate it, the IPv6 packet in it, send it across, and then it will strip it off and send it back to the back side of the IPv6 network. We've got some address resolution that has to take place with our systems. And there are a number of them. We need to find the physical address. The Neighborhood Discovery Program protocol is used for IPv6. The logical addresses, we're going to use DNS, hierarchical and authoritative. The first one I want to look at is to find the MAC address. And I'm going to go back to the command prompt, because remember, when we get into the network, the unique address is going to be the MAC address. So if we use the ARP protocol, I use an ARP-A, it tells me all of my IP to MAC address relationships here. Though, let's see. Let me find. This is the real one. These are some 62.1. These are all virtual addresses, and then I have a 169.254 down here. But 192.168.1.27 is the actual IPv4 address of this guy. So the default gateway, yep, it should know that. It's got its MAC address. Dynamic means that it found it automatically using the ARP protocol. .23 is a device on this network. It's got its MAC address 62. So the devices themselves are here, finds them dynamically. They go into a cache, and yes, they do timeout. Each of the operating systems are a little bit different on the timeout. They don't last that long. I think Windows is somewhere around 1.5 minutes if it's not reused. Other things down here, 192.168.1.255, my broadcast address. So it relates to a broadcast MAC address, and this one is static down here. I have some multicast addresses that are used here, and then a broadcast to any address. All 255s is broadcast to any address that's on the network, whether it's on my network or not, is again all else, because MAC addresses or switches are going to forward the hardware broadcast address out all of the ports. So ARP associates an IP address with a MAC address. It takes an IP address, finds a MAC address, so it can deliver it to a location. A gratuitous ARP is when usually when a system comes online, gets an address, maybe gets a DHCP address, it sends a gratuitous ARP out just to see if anybody's got its address. This is also something that's used in man-in-the-middle attacks because, yep, I've got an IP to MAC address correlation. ARP's pretty simple, pretty stupid protocol. So a man-in-the-middle tells everybody on the network that its MAC address is the default gateway. All the traffic now goes through the man-in-the-middle. So can be used against us. DNS lookups, DNS servers, the domain name system. We have the fully qualified domain names, FQDNs, mail.corporate, www.leaderquest.net, learning.leaderquest.com, different things that are fully qualified domain names. And I'm trying to start my server here. I want to demonstrate show you what a DNS server looks like. But a host, subdomain, domain, TLD is a top level domain. Those are the .com, .nav, .mil, on down the line. DNS server, authoritative name server. If it's an authoritative server, then I have the authority to put names into it, to make changes to it. Secondary name server, we keep a copy of it for backup. We can't make changes to it. It is a read-only copy of this thing. And then the root name servers, the heart of the DNS system, contains a list of records for the DNS root. This thing has started. Let me drag it over. This is a virtual Windows server here. And if I can get into the administrative tools and look at DNS, it caches lookups. I could put my own records in here, forward lookup zones and reverse lookup zones. Forward lookup zones is typically what we're going to use. I have a root here and then a bunch of top level domains. Under the top level domains, the comms, and these probably have all timed out. We got Google, let's see, I think I got LeaderQuest in here. Nothing shows up. Let me see if we can make LeaderQuest show up. It'll probably make me a liar. It's not being very happy, is it? Ping could not find. Yeah, it's done that to me before. Let's try. And it may be the it's not going to find that one either, is it? Should have turned this thing on and let it warm up before we started. Let's see if we can get to the default gateway. No, okay, so I'll look at it when we do the break and come back and do this again, but we have top level domains, the .com, whatever. We start with the root, go down, and then in the individuals here, 1 and 1 has a name server here which would list specific resources to get there. I will when we go on break here in a minute, I'll see if I can't get this thing running. It looks like my NIC got uncoupled from my virtual NIC got uncoupled from my physical NIC. Root name servers, I have zones, top level domains, list these things. The DNS records that are available, the record names, the A is an address record, a AAA is an IPv6 address record. An address record represents a resource. CNAME, canonical name, when we may want to use two names to look something up. We may want to use something else for that name. So the canonical name would then send it to the actual A record to get the IP address. MX is a mail exchanger, an email server. NS, a name server, where we get those things, and I'm going to have a process here in just a second, then we'll take a break. A pointer record is a reverse lookup, where instead of using a fully qualified domain name to get an IP address, we use an IP address to get the name of it. SOA is a start of authority, where we start with our authority, and SRV is a service locator. Things like Microsoft Active Directory would be in that. The lookup themselves, what I was trying to show, and see if we can get it going here in a minute, is this is a recursive lookup. Recursive lookup, I go to www.leaderquest.com. First thing I'm going to do is in my computer, I'm going to look into my cache to see if it's there. If I've been there before, it's going to show up in the cache, and I just use that IP address. If it's not there, I go to my local DNS server. If it has it, it sends it back to me. If it doesn't have it, it starts what's called an iterative lookup, iterative queries. The first thing it goes is to the root level, and I'm going to leaderquest.com, so it'll go to the .com, actually it goes to the root level itself, and says, can you tell me how to get to www.leaderquest.com? It sends back I don't really know how to get there, but why don't you ask the .com top level domain server? It sends me back the address of the .com server. I go to the .com server. How do I get to www.leaderquest.com? I don't know, but I can tell you how to get to the LeaderQuest DNS server. It gives me an IP address for that. I go to and this one will be the LeaderQuest DNS. LeaderQuest, how do I get to www.leaderquest.com? It sends me back the IP address of the www server, the resource. It goes into the cache, which you did see on my server, and sends that IP address to my workstation. My workstation puts it in its cache and then goes to that IP address. So, let us take a break until, let's say, and continue with this. So, address assignments, and the address assignments that we use, static, dynamic, and stateless address configuration is something that we can do with IPv6. Static is when we would go in to the device, and we can look at that on this virtual machine, because that's what has been done to it, even though it's decided to not communicate with me tonight. Go into properties here and go into the properties of the NIC, and either IPv6 properties here obtain it automatically, and then the preferred DNS server : 1, which is the local, the 127.0.0.1 equivalent. Properties here, I've typed in the 192.168.1.250 address, so 255.255.192.168.1.1 for the default gateway, and then the preferred DNS server 127.0.0.1, which is this computer. So we can get it statically. The other way that we could do it is here, obtain IP address automatically, which would give us a DHCP address. And on this one, it's probably going to give us a because it's trying to get there. It's not got physical connectivity to my physical NIC for whatever reason. I'll have to troubleshoot that one. But to get them dynamically assigned, we would use a DHCP server. I'll do this, and we're going to have some slides here in a second on DHCP. But the DHCP server has things called scopes. We have a scope here, 192. Let's go ahead and delete that scope and go through the create a scope process. So I'll go in here and do a new scope. The welcome wizard, we'll call it demo scope. That's just so we can keep track of it. The starting IP address 192.168. It's the keyboard 192.168.1. Let's say 200, and the ending address 192.168.1. Let's say 220. Very small group here. It automatically detected 192 is going to be a 24-bit subnet mask 255.255.255.0. We could change that here. Add exclusions. Exclusions are any addresses that are in that range that I don't want DHCP to hand out. If I did a whole range and had a default gateway in that range, I would put the default gateway address in there. If I had servers that had static addresses in that range, I'd put that range of addresses in there. You can either do exclusions or just don't put those addresses in your range when you do it. A lease duration, you get a lease on an IP address, and Microsoft's default is 8 days for that. DHCP options, we'll look at those. The default gateway and the router. I did that again. Trying to use the keypad and it doesn't work. 192.168.1.1 would be the default gateway. DNS server. I can put in a DNS server to resolve IP addresses, obviously. We can add that. A Win server, you don't know, that's a Windows Internet Name Server. Do I want to activate the scope? I'm not going to, because it might try to give out addresses. So we have the scope, and in it we have the address pool, the address leases. The other thing that we can do are reservations. If we do a reservation, we name it the address that we always want a particular MAC address to get. So we have to put in the IP address that we want it to have and the MAC address of that device so that it gets the same address all the time. But DHCP, automatic addresses or dynamic assignment of addresses when we do that. Stateless address configuration is when the router is configured with the prefix, the network address, and it has a stateless configuration statement in it, and the workstation then takes the prefix, the network address, from the router and generates its own host portion of the address. So it generates the host portion of the IP address. The DHCP assignment process is frequently referred to as the DORA. D-O-R-A. Discover, offer, and that's the packets over here. DHCP discover, which is going to be a broadcast packet, which means that it can't go through routers. So it broadcasts, and every DHCP server that hears this broadcast is going to send an offer. The offer is going to be a unicast message. The DHCP request is going to be a broadcast message. In case more than one DHCP server answered, it'll know that we didn't take it. The request requests the address that was offered to us. So we get offered an address, we request that address in a broadcast. Then we get a unicast back to acknowledge from the server. Says, okay, I offered the address, you asked for an address, I offered the address, you said you wanted it, so you can have it, the acknowledgement. So the DORA, discover, offer, request, and acknowledge, the four-step process in getting a DHCP assigned IP address. So, assessments, so we don't really need to record those. The Module B core protocols talk about IP packets, UDP, TCP, and a little bit about ICMP. Not a tremendous number of slides in it, but the IPv4 packets, we got the header and the payload, and I said I wanted to, and I do want to look at some packets here to see what this business is. This is header payload, and then TTL2, 321. What that's saying or trying to say is that we have a header information, and under the header we're going to have the payload. And the payload, we talked about the OSI model, and we had an encapsulation, so that header information got added as it went down the stack. My Wireshark is starting a little slow while we're here. Let me see, and I think I've got a DHCP in here, and it actually is the old boot P protocol, I thought. Boot P, yeah, and this is an actual coming off of the network. The discover packet here, if we go down here and look at it, Ethernet, the destination is the broadcast. The Ethernet down here, we have the protocol, UDP, so it's a UDP packet. We have a time to live in here, flags, differentiated services. The source 0.0.0 is at any IP address, and the destination is a broadcast. So we had the discover, which was a broadcast. The offer, you notice, comes back to the destination is the Dell computer. The source, the Belkin router here, that was what was the DHCP server. And we have the source address and then the destination. The destination is the address that's being offered in the process. The DHCP, if we go down into here, the DHCP offer, your client address 192.168.100.150, which is the address that it sent it back to. The request here, you notice, again goes to the broadcast, so that if two of them said yes, then it knows that it didn't get it. And then the acknowledged is a unicast that says, yes, you can have that address. I think this one may have some traffic on it. When we look at the traffic here, we talk about the header. We have the Ethernet header that goes on, and we looked at that, it's got the destination and the source address. The IP protocol It's got its information in it, and it's got its flags, and it doesn't have very many flags, but these are things that it's going to look at. Differentiated services field, which would be a quality of service thing. And then down here, the destination port, this doesn't really have any data in it because it's part of the three-way handshake. But we have a source port and a destination port. And then any flags that have been set here. And this one has a SYN set. We have a SYN ACK, and then an ACK. Let's go down here. Let's look at this. This one actually has some data down here that says you can sort of see its subscriber service on down the line. But it has the header information, and each of them has header information on it. Ethernet header is in front of the IP header, which is in front of the TCP header, and underneath that we have the HTTP information that is the data itself. The other thing that it talked about in the IP was a time to live. This one's 64. Time to live is basically how many routers it can go across before the packet expires en route. So we have the information here that we can see when we talk about these things. So we do have in the packet, we have the header and we have the payload. We have a TTL, a time to live, and this is showing that the time to live gets reduced every time we go across a router. And we have the version, header length, and if we go back to this thing, protocol, identification flags, if we go back to it, and I don't think that I can get both of them on at the same time, we have that information. IP version 4. And then we have the header length in here. The header length right here, 20 bytes. The DSCP, which is the differentiated services field in here, but it doesn't have anything set. Differentiated services field, the total length here. Identification is going to be a hexadecimal number. Any flags that are set on it, we have the flags, and then we have our, if we have a fragment offset, if we have fragmentation, fragment offset would be in there. And then we have the flags, the time to live under the flags. After that, the protocol, this one is TCP, which happens to be protocol number 6 when we do that. Protocol, the header checksum, it said it's disabled, and the header checksum unverified, and then we have the source and destination IP address. After that, any options, it doesn't have any. And then after that, options, and then any padding that we would have, then we would follow with the payload. The payload includes the TCP. And TCP is the next thing that we're going to talk about, so we might as well look at it while we're here. And it talks about what is, actually the next thing that it talks about is the IPv6 packet structure. And I see, it is much simpler. Ethernet, IP protocol, IP message when we look at it. So the IPv4, 32 bytes across on this thing. IPv6, 32 bytes, 128-bit address field in it, version, traffic class, flow label, because it uses flows, which is a continuous flow from one to the other. The header that goes in it, I think that this actually, we'll look at it and see. The TCP features connection-oriented, reliable, error correction, flow control, and sequence. And what makes it that way is where we were originally, if I can get back to it. The TCP, the three-way handshake here, we have the synchronization packet, starts a sequence number, a numbering system, a SYN ACK after that, and then an ACK. So we have these things that establish the connection. That's what makes it reliable. When we start sending data, we get an acknowledgement here, and then we get a sequence number, ACK whatever. It's going to acknowledge receipt of the data. Error correction, yeah, maybe error or flow control. it does that. It sets a window size, how much data we're going to accept at any one time when we do these things. You notice the window size here changed a little bit with 5840, 8192, and then we agreed on a 5840 for the window size. A negotiation process goes on there in order to do that. It does flow control, sequencing based on the numbering system, so that any data that's received out of order can be reordered. Any data that doesn't get there can have a resend. And this is the three-way handshake, the send, SYN-ACK or ACK-SYN. Actually, ACK-SYN should be the order that they go in. It acknowledges my synchronization and then starts its own. The way it sends data through this is this thing called a sliding window. And if I can find it here, I've got a little sort of demo for the sliding window. I got to close a bunch of stuff in order to get there, and then they pop up on me. And my everything is working very slowly tonight. That's why. I guess I'm slow anyway, but everything is really slow tonight. Anyhow, sliding window demo. What TCP does is groups things together. And it creates a window. And this one's got like 4 in the window. We can change the window size here if we want. We can make it larger, more data at once. Or we can make it smaller, less data at once. Retransmit timer. This one's got a 0% loss. So if we start this thing, we send data A, B, C, D. We send our 4 elements of the window. Once it gets the data, the window slides over. We get the acknowledgement. We send the other data. The acknowledgement comes back, and once that happens, we send the data. So the window slides over as the receipts get there, and we can continue to send information. Want to restart? Let's go with a high loss. Let's go with 20% loss on this thing, and see if it'll start. So we sent some, it moved over because all the data didn't get there. And we got an acknowledgement of 2, and now we send some data up and we finally get the 3 of them, it moves over. So it only sends data as it gets acknowledged and the window moves over, hence the sliding window, to send the data as it is needed, as it is required. I'm going to get out of this one because I'm just about to overload my machine, I think, with all the things I've got open. So the sliding window is sent and acknowledged, sent but unacknowledged. It does not slide over until the data does get acknowledged on the system. So that one was pretty cool. So the Module C here is about network ports and applications, and ports represent applications. HTTP, port 80, is the well-known ports. They got the name well-known when there were 3 computers, 4 computers, 5 computers in the world, and somebody wrote this, and there weren't very many people working on them, obviously. It wrote this really cool program and said, hey, try out my new program that I wrote, HTTP, to be able to transfer information, and you can find it at port 80. So the ports became well known, and we use the very lower port numbering as well-known ports when we do that. We still use those today. So, and then we're going to talk about TCP, UDP ports, common network applications and services, and common standard network ports, and then some TCP IP troubleshooting tools, things that you probably may have used already. But network ports here, web browsers, FTP, Telnet, clients, inserted a little help over there for what we do. Down at the bottom, the system ports, the well-known ports 1 to 1023. User ports 1024 to 49154, and then private ports, which are also called ephemeral ports, 49152 to 65535. So we have 65,535 of them. The source has to have a port, and the destination has to have a port. And we'll go back to this thing. Let's see if we can find the HTTP here again. The source, we'll go down here to the TCP, the destination. See, this one's different, 88, and that's what gets me, 8895. And the source port is 45662. It's a subscribe something, so it's going to a unique port. Let's see if this one gives us a little more standardization. Source port, destination port. It's the return of it. So it's not being very helpful, is it? Let's see if we have anything in here that's standard. If I want it to, and it's not going to, I'm not going to get anything that's going to be a standard port on this, am I? No. Well, HTTP, the destination should be 80 on this, but it's not. It's an odd one because it's doing something else. We can obviously use other ports to do things with, and maybe if I just did something really clever like use a different one that I have standards on, but we're doing Wireshark. But the standard telnet port here is going to be 23. HTTP is 80. FTP is going to be 21. Let's see. I got one here that just says traffic. I wonder what is in it. Maybe it's got something that'll stand. It's got a lot of IPv6 in it. It's got some multicast. 224 is going to be multicast addresses. Got ARPs, a little bit of everything in here. And this one's not going to be a standard either, is it? Destination, nope. Well, that didn't work out. See, these things are all going to something odd, not the actual web page itself when I do those things. So I'll see if I can find one in a minute that's standard, and we'll come back to we'll come back to these. But the ports that are listed, FTP 2021, and if you look at the objectives, it gives you a list of ports that they want you to know, and those are ones that you should know. Email ports, SMTP, Simple Mail Transfer Protocol. It's the sending port. It's going to be port 25, SMTP, and it's one that's not on here. Post Office POP3, port 110. It's a receiving one, and IMAP is also a one that receives messages. And then the MAPI protocol, not here, but IMAP here is 143. Different protocols that you may need. Remote access protocols, Telnet 23, SSH over here is 22. RDP, remote desktop protocol, not on here. It is port 3389. VNC, I think it's port 5500. It's a kind of a commercial version of remote desktop. Allows a little bit more flexibility, I guess is the word that I'm looking for. HTTP is going to be port 80. HTTP, TCP port 80. SNMP is going to be UDP port 161. It actually is 161 and 162. Has two ports in here. resource sharing, LDAP, NetBIOS, SMB, SMB, and let's see, FTP, TFTP, NTP, different ones. NTP Network Time Protocol is port 123, and it is on here. TFTP Trivial File Transfer Protocol, TFTP is port 69. Server Message Block, SMB, is not on here, and I don't remember it, and I don't remember LDAP either, but those are also resource sharing, the way that we can send information from one to the other. The tools that we talk about, IPconfig gives us a lot of information. That's one that I can go back to this thing and I think maybe make a little bit of sense out of. The first one, if we do, and it's got a lot of IPconfig gives me basic information about my address. I have an IPv6 address, a link local address, an IPv4 address, subnet mask, default gateway for both IPv6 and IPv4. It has some other functionality. IPconfig all gives me more information. So when I look at the all, you can see just from the list here, there's more information, including the MAC address, the DHCP server, where the address came from, different things that may be configured on it. Config display DNS. When I said that, and this is all of the lookups that this machine has in its cache, that if I go back to any of these locations, I don't have to go to a DNS server. They're in my local cache when I go there. And here's a blockage, anycast.dropbox.com. So I've got an anycast. I've got Dropbox on it, obviously, so it's communicating with Dropbox. You can go through this as a pretty long list here. Different things that have been looked up that get put into the cache configuration of the device itself. So the IPconfig command and then the what is available / question mark gives you the what you want to do with this thing. You can renew and release IP addresses, do a number of things with it. But IPconfig, one of the things, what's wrong with my local machine? What's the state of the networks? Am I getting an IP address? Those kinds of things. NetStat tells us every connection, every port that we are connected to. And I guess that I should have left the command prompt on. And I never remember it switches. So / question mark -A displays all the connections and listening ports, displays all the executables, displays the Ethernet statistics, fully qualified domain names for foreign addresses. Oh, let's just see if it tells us anything. -F. So we have some established connections, and these are all local. I have an HTTPS here to 192.168.1.127 to 162.125.34.129. Established connection, so you can see what you're connected to with these things. So Amazon Web Services, and it's got a close and a wait. These have been closed and we're waiting. I have an established one here. BingForBusiness.com. Lots of things you can see that open up that you may not have asked to open up, but they are there. DNS lookup actually is a way to check the DNS server. You can go into a non-authoritative server, the address, and it's going to show us whether our DNS server is working or not. Ping, you probably use. Ping is a layer 3 protocol. it will check connectivity at layer 3. It doesn't mean that the application is going to use. And Joe says ping-t if we want more than 4. Ping-t, we can specify how many pings we want to go across the network. Traceroute uses that time to live in order to find all of the routers between us and a different location. What it does is starts out with a time to live of 1. Goes to the first router. The first router says, hey, once I take that away, I have a time to live of 0. Sends back an error message. So, okay, I found the first router. Then it does a time to live of 2. Goes to the first router, goes to the second router. Second router sends back an error message. So this thing finds all of the routers between us and the destination by leveraging the time to live and using the error messages that come back from those devices. This one down here is a path ping, which is a Microsoft thing that kind of emulates a trace route. It gives me all of the locations from one to the other, and then it gives me some statistics down here. RTT is round trip time. How much time is it taken if it can calculate it? Lost and sent. Any packets that have been lost, sent. What's the percent of these things? What's good, what's not good? And this is loss 0, and here we have 100% loss at this one location. And that may be that it's just not playing. Some of the some devices, probably like your router, is configured not to respond to certain ICMP messages. So this one is to match, and I think that the one on the right does it anyway. Yeah, here we go, match, and I'll just go ahead and put the answers up. SSH 22 LDAP, the one that I couldn't remember, 389, I should have been able to remember that. SMTP, Simple Mail Transfer Protocol, the sending email, port 25, IMAP 143, DNS 53, Telnet 23, HTTPS 443, and POP is going to be Post Office Protocol, port 110. 2 receiving protocols, POP and IMAP. IMAP actually keeps the emails on the server, so as a network administrator, that's where you want them to be. Certain circumstances, you're required to keep a backup of all of the emails. POP downloads the emails to the local machine. There's a configuration in it where you can leave a copy on the server if you want to, but in an enterprise environment, you want to use IMAP because the emails stay on the server. You can make backups of them. The user gets to read them. They can download a copy of them, but you can't delete them from the server using the SMTP, the IMAP protocol. Your company's custom server software application needs a TCP port to listen on. What port range should it be configured to use? Anybody? Oh, did I get a B? System. You can actually get a system one, but they belong to things. User, and the user ports are going to be the ephemeral ports. They're going to be the top end, and they're the random ports when we connect to a well-known port. They talk about private ports. I've always heard them called well-known ports. System ports, okay. And I think they actually I've heard those called reserve ports, and then the user ports, random ports, or ephemeral ports that anybody can use. What we do when we connect from an IP address to a port, we actually are having a socket. So a socket is a combination of IP address and port number when we do these things.